Greetings and welcome back to the lab, and welcome to Musical Monday. That's what I'm going to start calling this series, where we talk about the keyboard. That's actually the sound module, the oscillator module. This here is Keyboard Junior, which was an original test for this project, and this is where we've gotten so far, is an actual keyboard made from PC board parts and electronic components, and a little bit of hardware, but more on that later. All of these parts are available on my website, or rather I should say all of the design plans are available on my website, which will be linked below, or I'll even put it up on the screen right now. It's BitNotes.com. Just go there and look for, scroll down a little bit and you'll get to the shop, and in the shop I have actually the designs for download. It's not a purchase, this is open source. So if you're not familiar with the project, ultimately I've been interested in electronics and music for many, many years, and I finally decided to try and do something musical. It started with me buying a kit last year that was just so not musical. It was not funny. And they called it a toy piano. It was a bunch of buttons. They didn't make anything even remotely in tune. It was just random resistors controlling timers and stuff like that. And that, oddly enough, is what I'm doing here, is resistors controlling timers. But ultimately, I decided, let's see if we can't actually build our own keyboard. And I started with the keys. I just said, where am I going to get a keyboard? And I mean, I see all of these other YouTubers who have their keyboards, and I don't know where they're getting them exactly. Maybe I haven't watched enough of their videos yet, to be fair. But ultimately I said, I bet I could do it myself. And I ended up embarking on that, trying to figure out how to do it. This is PC board material. It's just only a millimeter thick. And on this switchboard, there's a bunch of tactile switches, and okay, so it makes some noise, but just in pressing the keys. Also, actually, the black keys do work, and the bigger keyboard actually has them lifted up a bit. This is just Junior. This was a first prototype, and I plan on using that to work against the prototype of the oscillator board here, which I started building and I ran into problems. But ultimately what this episode is going to be about is this oscillator board and what I figured out about what went wrong and why it wasn't working for me. And it's going to be a fairly long episode, I think, because I'm going to go through all the troubleshooting and try and get this thing built out to the point where I can hook up Keyboard Junior to this, which is not exactly how I plan to do this. There will have to be a revision of this board because I already know about a wiring problem. So ultimately, this board will be redesigned. I'll have to get the new prototype in, and I'll have to be able to build it. But while I'm waiting for that, I'm going to do some testing here and some troubleshooting and figure out what other features I need for the newer version of this board. So let's just launch right into this. The problem I had with this board had to do with, you know what, I'll bring up the render of the board on the screen because it'll be a little bit clearer to look at. But if you look down in the bottom at the middle, you will see a header that has 10 pins on it. Those 10 pins are the interface that goes to the actual keys. With that interface, I can put power into the keys, and then each switch I hit returns a signal. The problem I ran into was I was trying to apply power to the board up in the upper left-hand corner where I've got another header, and there's also a corresponding header in the upper right-hand. I was trying to think ahead as far as if I need to connect power from one of these oscillator boards to another oscillator board, then I need to have the ability, without making a super wide extension board of some sort, to connect the boards together. So if I have the same header on the left and the right, then I can make a small little board that joins two of them together and then just string them together like a chain. So that was the idea with that. There is power on that interface. There is power on the interface at the bottom. They were not connected to each other. And I was injecting power on the upper left, and it was not making it down to the middle on the bottom, where it goes to the actual keys and then gets switched back into a signal here, which then goes through the rest of this oscillator board. I hope that makes some sense. I'll try to put some degree of animation into this so you can see what I'm talking about. So the ultimate solution, let me come back from the render here, is I ended up putting a bodge wire, and I'm not sure how clear that's going to be, so let me see if I can't point it out in reality. That is going from the positive pin here to the positive pin up here. And I later realized there might have been a slightly more efficient way to do it, but ultimately that will all be dealt with in the redesign of the board. It won't look a whole lot different than it does now, and so that's why it's worth actually going through and trying to do some more troubleshooting with this. But let me go ahead and hook up my breadboard to this and a power supply and prove to you that it actually does make sound. Okay, now we're back. Let's take a look at what I've set up here. And I just tested it off camera to make sure it actually was working. I've got power coming in. I'm only using the breadboard here for a little adapter that allows me to get the power off of the USB. So this is actually USB powered. I've got the power going into that header that I was talking about here, and that will then come down to here, and I'm going to use the positive down here to bridge to the pin here that actually associates with switch 1, which is this very first oscillator. There are 8 oscillators running across here. So just to prove that it works, this was supposed to be a 261.625 hertz signal, middle, 1 octave below middle C. We have sound. That proves that it actually does work. Now, we need to talk about a few of the different problems that we have here and start working on solutions. Number 1 was the problem that I had with the power not going from here to here. Number 2, once I got that working and I got sound out of it, it sounded horrible, and then I realized I hadn't put in my decoupling capacitor yet. That's what this second capacitor is. That is important because it filters out or it prevents random frequencies from making it into the circuit. And if that happens, then you're not listening to the intended tone, you're listening to a combination of that and any other tones that manage to work their way in through interference. So putting that decoupling capacitor in solved that part of the problem. The next problem I had, there are 3 resistors here. These 3 in combination, let me make sure I'm seeing that right. 1, 2, oh, sorry, yeah. If you look at an astable circuit for, let me actually use my dry erase markers here and go over to the board. And let me actually get rid of something that I was working on. So generally speaking, if you look at an astable circuit, and I don't want to get too much into the theory, you're going to have an R1, an R2, and a C. And that C is this first one here. R1 is this first resistor. Let me grab the pointer. This first resistor up here actually represents that R1 that you usually see. What I did for R2 was I broke it down into R2A plus R2B plus R2C. Basically, I broke it down into 3 resistors. The first 2 are up here on the board, side by side. The third one is this adjustment down here, this potentiometer. What ended up happening, and I'm trying to come up with a better sort of solution for it, was ultimately I had planned for this to be like the last 1% of adjustment, so you can fine tune it to get to your frequency, your target frequency for the note that you want to play. But ultimately what ended up happening was my 1% accurate resistors are not actually 1%. My 22K resistor that I had came out to be 21,500. If you work that out, that's a little over, well, it's not 1%. Let's see, let's grab the calculator and see. Let me actually disconnect this so I don't drop things. We'll grab the calculator and let's take a look at how we do the math on that. I could write it down here, but it's going to be a little hard to see. So if we think about 22,000 minus 21,500. Those of you that are math whizzes have already figured this out. It's 500. Well, 500 divided by 22,000, that's my difference from my target, is 2.27. Now let me just multiply by 100 and that'll be even more clear. 2.27272727 keeps going, 27. It just rounded at the end there. That's 2.25%. That's not 1%. Now, I mean, for a lot of people, an extra 1% is not a big deal. But what ended up happening was I had two resistors that when combined were supposed to achieve a particular resistance, which was the design resistance for R2. And it was supposed to get me within 1,000 of the target, and this is a 1,000 or a 1K resistor, so that I'd have that fine-tuning adjustment. Well, all the resistors ended up coming up short and by more than 1%. So it's actually too low to get me to my target frequency. And when it's too low with R2, you end up with a higher frequency. So I kept adjusting. I got close, but I could not quite get there. So I think the solution ultimately for this one, and this is, it may be obvious to some people, but I think the solution is going to be, before I actually solder the resistors to the board, put them on a breadboard or something like that so I can actually measure the resistance and make sure that they are close to within the spec. It's really unfortunate. I bought a bunch of resistors that were all supposed to be, let me cover up the name of the manufacturer here, but you can see 1/4 watt, 1%. That's what they were supposed to be. They were not. So that's where we are on that one. That takes care of that problem. Now the next problem I have is figuring out the output is very loud. I was actually thinking it was going to be not loud enough, and I went and I got a Bluetooth speaker which had a line in, thinking that it would be a low and that would take care of the amplification for me. It's actually too loud. And so there is a provision on the circuit board for mixing, and that's this last resistor in each one of these. And that's supposed to knock the signal down, but as it turns out, that interferes with all the other resistors and changes the frequency. So I would have to carefully tune everything to the point where they're all at the same volume level while also achieving the same pitch, the same frequency. So I'm going to have to abandon this and come up with a solution to that. So that's where we are at this stage. And what the rest of this video is going to be is me explaining the next problem and then going away and coming back instantaneously for you and having a solution for it. So that's our problems. How do we deal with the amplification? Can I add another component where that resistor is? What is my solution going to be, and what is the modification going to be to this circuit so I can have more of these prototype boards made? So I'll be back in just a moment. Okay, so now we're set back up again. Let me clear what I've written down here before and go over what we're going to do. First thing I need to do is just demonstrate to you the problem that I'm having. So let's throw in, if we have our output, represented by a couple of little blips here. This is normally ground, and this is the signal coming in. And I can either just take this out and go to a speaker. Pardon my crude drawing here. I can either just do that, just straight to a speaker, or that is what you've heard so far. If I get rid of the speaker and we add in a potentiometer, and let's say this is the wiper here, and that goes to the speaker. Same thing. There's your speaker. There's your other connection. That is what I've currently got it configured for. It is plugged in, and the only thing is I just didn't want to have the tone constantly running, so let me demonstrate what this sounds like. Now I can take my screwdriver and adjust this, and you will hear the pitch change. But it's also getting lower volume, because I'm basically sticking a resistor in and it's resisting the force of the sound. Now that's not what I want, because that means that when I turn it down I also change the pitch. So I want to try something else. So my next idea would be, let's try and I'm trying to go sort of one component at a time here. Now if I take out the resistor and I insert a capacitor just straight in, this will be represented by, wow, this really is a crude drawing, isn't it? I need to come up with a better method. Here's your capacitor. Wow. Okay. Let's just see what that ends up sounding like, if it's a lower volume or not, or if it's completely blocked. And just to prove that this is correctly set up, if I plug in at the beginning of the capacitor, oh, I see what I'm doing wrong here. That is correct. I do want to be plugged into ground here. And so, okay, so I see what I've done wrong here. This wire is actually what's connected to the speaker. So that is running through the capacitor. The capacitor is blocking it completely. By the way, at full volume, it's distorting on top of everything else. So the capacitor did not work. Another idea I had was to throw in, well, I could put both. I could put the capacitor and, oh, wait a minute. I see why that didn't work. Let's try the capacitor again. After I move this wire over one, and still no sound. Now I can take that, and I can take the resistor. Now at some point I'm going to hit filtering. I'm going to get a high pass or a low pass filter in some combination here. That is not my intention. Let's see, wait a minute, did I do that right? Yeah, it's coming out of the capacitor into the middle pin of the resistor, and, well, actually, now that I think of it, the capacitor was blocking the sound altogether, so anything I put after it has to be stricken out. So maybe let's keep track of that. So series cap, that's failure. I'll just put an X next to it. So we know that that's not going to help us. So this wasn't going to work anyway, and actually on top of that I did it wrong. That should be connected here. I don't know why I keep moving my ground. That is connected into there. Let's just see if we get anything. Nope. And I apologize you can't see it because my hand's right on top of it. But no, we got nothing out of that. And that's because the capacitor is blocking the signal. So now the next option would be, let's take the capacitor and let's run it to ground. Just spread it out a little bit here. Let me draw this out for you. So what I'm saying is I've got my inputs. I've got my signal up here. My signal is then going through a capacitor down to ground. Now this is ground, and this, oh yeah. So then we'll take off of here and off of here and hook those up to our speaker. As far as I can tell, that should charge and discharge the capacitor. So let's see what that ends up sounding like. Here's, yeah, that is, let's see, signal's got to go from here to here, and then the speaker can connect in there. Still just as horrible. Alright, so that didn't work. So we're going to call that, I guess that's a bypass capacitor. Okay. What else have I got? I can play with a diode. That was another thought that I had. Let me get, I just have some leftover diodes from different things that I was working on. Don't want to dip into my regular supply. I know this should, the last time I tried this, it worked. So let me take the diode and stick that in series. So I'm going to have, okay, the more positive side is this side here. I'm going to put the diode in this way. Now, in theory, what would happen is that your diode, what am I missing here? Oh yeah, there we go. The diode would actually drop it by a certain amount of voltage, assuming you bias it in the correct direction, because diodes are polar. They have a polarity to them. So let's see what happens here. See, now that is reducing the volume, but I think it's a different pitch. Something has gone wrong because I didn't have that much distortion before. Huh. Alright. I'm going to go away and come back in just a moment. Okay, I'm back, and I think I figured out what was going wrong. I double-checked everything. The wiring was fine. But I think the problem was that, in part, yesterday I was using the original board that I have. Actually, let me grab the right one here. That I had already wired up, because a lot of these lines are going to be more reliable than these wires here. So, and the connections, the spaces between the connections are shorter. So, that was part of it. And then it also occurred to me, all right, the idea with, and I called it actually, earlier I called it a bypass capacitor. It's actually a decoupling capacitor is what I meant to say. And so I was thinking, okay, wait a minute, I said that wrong, decoupling, hey, wait a minute, what about the decoupling capacitor here? So I increased the decoupling capacitor, the capacity, the actual capacitance. That's not in the original design. When you talk about R1, R2, and C, this is a different C, a different capacitor. So I increased it from 0.1 microfarads up to 10 microfarads, and I'm getting a much cleaner sound now. It warbles a bit, but just to demonstrate how close that is to the actual sound I'm looking for, I have the sound on my computer, and I'll tell you later how to get that. I just did it in Audacity, but if you look for certain frequencies on YouTube, you can just say 440 hertz square wave, and you'll get an A. That particular A. 220 is an octave lower, and so on and so forth. But you can find those on YouTube. But what I've done is I've got it set up on my computer using Audacity. I just told it to generate a particular tone and did it as a square wave. So I'm going to play this, and then I'm going to play that. And if you listen really carefully, you should be able to hear a, well, we call it beats. And I think that term may have been used in other ways too, so not to be confused. But if you listen carefully, you can kind of hear a pulsing sound. So let's go ahead and try that. And we add in the computer. It's the same thing you get if you're actually tuning a guitar or something else and you have a reference tone. You're listening for that warble, and you're listening, you actually want to cancel that out. So you keep tuning what you're tuning until you hit the reference point, and then they'll be in sync. And so that's how I know I'm really close. Plus the fact that I also happen to have an oscilloscope so that I can use that to measure the frequency, but then I'm relying on the accuracy of the frequency measurement on the oscilloscope. So anyway, let's go back to what we were trying to do before, which is, let's see if I add in, say, a capacitor. Let's just try this again. I believe what's going to happen is the capacitor is going to completely block the signal. Come on. Some of these older breadboards sometimes don't want to receive the pins you're trying to stick into them. And the newer breadboards start falling apart pretty quickly. Alright, here we go with the capacitor. And that's plugged in and not making any noise. Now let's try the capacitor going to ground. And I believe that's what I've got here. That's ground. So if I take the capacitor, send it to ground, I'm going to spread out the legs a little bit. And that, assuming it's plugged in. Yep. Okay, well, it's functional, but the question is, can I put a variable resistor in there? So that was the other thing I was trying to do. So series capacitor does not work. What I called bypass, and I meant to say, let's get rid of that. Well, actually, at the moment, the decoupling capacitor, I'm trying to make sure I get the terminology right here. The decoupling capacitor is functional. So I'm going to leave that in circuit. I'm going to take the output from here. I'm going to plug it into my variable resistor. And then we'll go from the, well, actually I don't even have to. And just take my output straight off of that. So let's see what happens. Interesting. Okay, either I've done something wrong. Alright, let's make sure this still works. Yep. And we'll plug in the resistor again. And try again. There doesn't appear to be anything there, but it could also be because I have it turned all the way down. I'm not sure what position this is in. So I'm hoping to get some degree of volume. Okay, I'm fumbling. I admit it. Alright, that's not helping. Going the other way is not helping. Now, let's pull the capacitor out and leave that in. Interesting. I'm trying to adjust it and find well, I'm going to go back down. These little resistors would be great for fine-tuning and then leaving it alone, but as far as testing, not the best option. Something has gone wrong here. Alright, I'm going to go away, and like that I'm going to come back with a better solution. Alright, well, sometimes you go to solve one problem that was unexpected, and you end up solving another. And I may well have solved the problem here. And it is considerably simpler. So here's the thing. I ended up swapping out the adjustable trimmer pot for a different style of trimmer pot, which instead of, this is like, I have to turn this thing 28 times to get the full range. This is just one time. And I don't know if you could even hear it. It's running right now. Now it's off. Let me go the other way. Back on. When I reduce the volume, it's not changing the pitch. And I don't actually have... Oh, I just knocked it out. That's why I haven't been using this one. It's not in the best of shape. But I don't have that decoupling capacitor here, but I have the new decoupling capacitor in here, and I think that may have been the problem all along, was it wasn't rejecting enough frequencies, and when I turned it down it was allowing different frequencies in, or something along those lines. But that means that basically I can take this and turn it down, which means I should be able to swap this back out for the more adjustable one and slowly turn it up and down to test it. That'll be my confirmation that that is working. So let me do that real quick and I'll be right back. Okay, that didn't take long to swap that out, but I've tried actually turning it, and while I can just barely hear it right now, it's not giving me much of a response. So it occurs to me to go back to my original plan, which was to put about a 100 ohm resistor in there. I'm not sure where I came up with that value, but that's about what I was figuring. So I've got some of my resistors here. Let me dig out and find the 100 or something close to that. And we'll just try some different resistors. There's a 220. There's a 120. There's 100. So yeah, it's just barely audible. Let's see if I can find a resistor in here that's usable for this. This should be a 100. I pull that out, I hear it go away. I put this in, I move this over. This is 100. Hey, lower volume. I hope you can actually hear it, but it's there. And it doesn't appear to have changed too much. So let's go back to the computer and play that particular sound. Now I'm going to have to lower the volume on that. And then play. Yeah, lower. Yeah, I can hear the dissonance. Okay, that may be difficult for you to hear. And at 100, I've knocked it way down already. So let me try putting in something less than 100. Let me put my resistors back. I'll be back in just a moment. Okay, I have sort of randomly picked 39, another value I happen to have. And that's, if you think about it, it's about a third, 2.5 times difference, so maybe it'll be 2.5 times as loud. I don't know if it works that way. But if I can get these lined up properly. There we go. Okay, that's a little bit better. So I could live with that. I could say 33 or 39, somewhere in that neighborhood. This is basically solving my problem. Let me play the tone again so you maybe can hear it a little bit better, the dissonance. Ow, that is fairly far off. Now I'm wondering if I've got this wrong and that changing the resistance is actually still a problem. Let's go back to the 100. Actually, the easiest thing to do is grab another 39. I'm going to put them in parallel. And if the pitch changes, because if I put them in parallel, 39 gets cut in half. The value of 39 gets cut in half. I don't think that's actually changing the pitch. Now, I mean, I could pull out the oscilloscope and really confirm it, but I think we're probably okay. So actually, I don't need a huge amount of resistance to knock this down. And maybe even part of the problem is the speaker that I'm using might actually be, instead of being like an 8 ohm speaker, it's a 2 ohm speaker or something like that. That could be something playing into it. It also occurred... Did it just go up in pitch? Something's messing with it. Yeah, I think that is... I don't think that the resistor is the problem. I think there are other things injecting more problems into the system. So let's attack that idea real quick. I'm going to leave this running so we can hear if there's a difference in pitch. Let me see about putting things away real quick. I'm going to leave that 39 in there. Put these away. Oh, crumbs. My address was on there. I'm going to have to blur it out. Alright, so another thing I haven't done yet, and let me grab my tweezers to do this a little bit more carefully, is I've got the original decoupling capacitor in there on top of the new one that I added. Now, I have read that if you put multiple capacitors in parallel, you can filter out more frequencies. Now, obviously, I don't want to filter out the frequency I'm aiming for, so I'm going to have to do a little research into that. But as far as I'm understanding, I should be okay to pull this. It is now pulled, and I don't think it's changed the frequency, at least not by much. And I still have this adjustment down here, and if my resistors are the correct resistors, or they have the correct resistance, I can still tune this. So I'm happy with that capacitor. I think we may have a solution here. So the next step, and I think we'll probably already have a long enough video. So next week, I think what we'll do is I'll start building this out, and I will add in the electrolytic capacitors as the decoupling capacitors with larger values, and use that to try and tune this bit by bit until I can get enough of it filled out to be able to use Junior. And then once I've got that worked out, I can make any changes I need to the circuit board, order them up, and we can build it finally. So this was bound to happen. At some point I was going to have some kind of horrible issue. And I mean, some of you are probably thinking, wow, this was such a simple thing, how come I didn't know? Hey, I'm not as experienced as other people. So let me turn this off before it becomes really annoying. But I want to thank you for sticking through all of this. I'm going to have some fun editing it all together. And yeah, until next Monday, more Musical Monday.